All right, so I guess we'll get started. So today's speaker is Patrick Brown from San Jose State University, and he's going to be talking about meteorology and climatology of wind and solar power droughts over Western North America. And I'll let you take it away, Pat.
Sure. Thanks a lot for having me, Nick, and for having me at the Physical Oceanography seminar at Woods Hole. I've never been to Woods Hole in real life, and so I'd love to come back at some point when it's not COVID and I can actually visit. So I have a meteorology, climate science background, atmospheric science by training, and I told Nick that I would try to, incorporate physical oceanography into this. And unfortunately, there's basically no physical oceanography in this talk today. We know each other from our PhD at Duke in the Department of Earth and Ocean Sciences. And in my PhD dissertation, did a lot of kind of ocean atmosphere interaction and dealing with the AMO and the PDO and things like that. And so there was some potential for this to incorporate those things. And there actually is an element of that in my research currently, but it's just not kind of ready to present. So I just apologize ahead of time for not a lot of oceanography here, and take full responsibility that that's my fault and not Nick's fault. But so you can see my screen, right? My title. Okay. So my topic here is, meteorology and climatology of wind and solar powered droughts over Western North America. And so I first just want to talk about why I'm interested in this. So this is kind of a new topic for me. This is my first study in this area, and I have a paper submitted, which is under review right now. But why am I interested in this? So it really comes down to the ascent of wind and solar power going forward in terms of powering society. And so that comes from, of course, concerns about climate change. And that's kind of best exemplified by the Paris Agreement. So the Paris Agreement aims to respond to the global climate change threat by keeping global temperatures, their rise this century well below 2 degrees above pre-industrial levels, and pursue efforts to limit temperature increases even further to below 1.5 degrees Celsius above pre-industrial levels. And so when we look at those goals and compare them to what climate models suggest would happen under various emission scenarios, this is from the year 1850 to 2300, global mean surface air temperature change. And this one kind of starts with a pre-industrial level at about -1. So at about 1, you're talking about the Paris Agreement goals. And so in order to stay below 2 degrees Celsius above pre-industrial levels, you're talking about one of these very kind of low emission scenarios, these high mitigation scenarios. So in this graph, it would be this like RCP 2.6 emission scenarios in order to get global temperature to stabilize. And so another way to look at that is, instead of looking at global mean surface air temperature from climate models, look at the actual emissions that would be required to limit global warming to various degrees by 2100. And so that's what this is showing. This is net CO2 emissions in gigatons of CO2 from 1980 to 2100. And so here's this like RCP 2.6 emission scenario. So this is saying that this teal line, emissions need to be dropping down and hitting 0 and then go negative sometime this century in order to stay below 2 degrees Celsius. And then it's been kind of trendy to go and say, no, we really want to stay below 1.5 degrees Celsius. And so in that scenario, you're talking about emissions getting down to 0 by about 2050, and then going negative after that for the remainder of the century. And so that's why you hear a lot of pledges now talking about net zero by 2050. And so we hear that the European Union has a goal of net zero by 2050. Japan just came out with a net zero by 2050 goal. China, I think, said 2060. You hear it from all sorts of corporations. You hear it at the municipal level. So all sorts of cities have net zero goals by 2050. And tomorrow, the Biden-Harris administration will take over. And according to their website, they have that same language. So they talk about an economy that will put the United States on an irreversible path to achieve net zero emissions economy-wide no later than 2050. And part of that is the power sector, the electricity sector. On their website, they say they want electricity to achieve a carbon pollution-free power sector by 2035. So very quick on the horizon. So if we look at, historically, what our power sector has been powered by in terms of the primary energy, it's of course mostly been fossil fuels. So this is US electricity generation by source from 1950 to 2019. And we see that historically it's been mostly coal in brown here. And then recently, since 2007, since kind of the fracking revolution, natural gas has taken over for coal, which has allowed our emissions to actually be reduced by quite a bit, because natural gas is much better in terms of energy produced per unit of CO2. And then we have kind of this nuclear fleet that's been more or less static. And then we have renewables, which have been more or less static because we're including hydroelectric in here. But renewables are poised to really expand in the future. And you can kind of see that here from just zooming in on the renewables portion of it. So historically, renewables were only hydroelectric. And then we have some biomass coming online in the 90s. And then recently, since the turn of the century, wind has really expanded by quite a bit. And then we're expecting solar to really expand quite a bit moving forward as well. So just at the very beginning of this potential rapid expansion of wind and solar. And so most plans going forward, especially the plans that are talking about decarbonizing the electricity sector, do something like this, where they're saying like, here's the electricity sector in 2015, mostly fossil fuels, coal, oil, natural gas, nuclear, hydropower, and then we are expanding that in terms of there's going to be more energy used from electricity because you're electrifying things like transportation and heating and ranges. And so it's not just water heating, but house heating and ranges and things like that. So you're electrifying those things. So you're expanding the total amount of electricity. And then that additional electricity is majority wind and solar in most of these plans. So that is why I'm interested in wind and solar power, is that it seems like it's going to be taking over a lot larger portion of the electric grid going forward. And one of the reasons for that is that we've seen a very large decrease in the cost of wind and solar power just over the last decade. So this is the levelized cost of energy for utility scale renewable power generation. And so each one of these, each color is a different technology. So biomass, geothermal, hydro, solar PV, concentrated solar power, offshore wind, onshore wind. And then you can see here in gray is the fossil fuel cost range. So this is the levelized cost of energy is, essentially summing over all of the capital costs and the fuel costs over some period of time and using a discount rate, and then dividing it by how much energy is produced. So it's a dollar per kilowatt hour. And so we see this historical fossil fuel range that in 2010, solar PV was way more expensive than the fossil fuel range, but now in 2019, it's on average, near the bottom of that range. And we see that large decrease also in concentrated solar power. And then offshore wind and onshore wind were a little bit ahead of solar power, which is why those kind of took off first. But you can see down here that solar and wind are now breaching that lower level of the fossil fuel cost, at least in terms of levelized cost of energy. So that means that in a lot of cases now, it's actually cheapest to add wind and solar over fossil fuels. And so that's one of the reasons why we're seeing this large expansion of these means of generating electricity going forward. But there are major issues with wind and solar power. And I think it's kind of easiest to see this using a diagram kind of comparing the wind and solar power system to our previous energy system. So, previously under our fossil fuel energy system, we have these power plants and we have the fuel, and the energy is stored in the fuel, right? Like it's very easy, or it comes pre-stored. The energy is stored in the chemical bonds of the hydrocarbons. And so we can put our power plants kind of relatively close to our population centers, and then we can burn fuel when the demand is high and burn less fuel when the demand is low. So if we think about this in like a typical week, so Monday through Sunday, 1 week, here's power. And this is, let's say, power demanded by society here, represented by just our Bay Area where I am. And so we have this daily cycle in power demanded. So power demanded peaks around 5, 6 p.m. when people come home from work during non-COVID times and turn on their lights and turn on their kitchen and their TV and their appliances. And at the same time, most of the offices are still running. And so that's kind of your peak demand. And then you have kind of a floor trough of demand at around 4 a.m. And so in our traditional system, you have kind of some baseload power that might be from coal, and nuclear is in there as well. And then you're able to have dispatchable or ramping power that goes up and down to meet the demand of society kind of on a second by second basis. But of course, this system emits CO2, which is a problem and makes it a not very good system in the long run in terms of sustainability. And so that's why, in addition to all of those goals I just mentioned previously, various states have renewable portfolio standard goals that say, the fraction of electricity generated by renewables has to be some level by some year. So California has a goal of 60% by 2030 and 100% by 2045. And so there's 29 states with these renewable portfolio standard goals, and more are coming online all the time. So there's definitely a push both kind of in the free market area of it costing less now to put in new wind and solar as opposed to new fossil fuel infrastructure in a lot of places, both in terms of that and in terms of top-down regulation. We are transitioning to much more wind and solar. So what is the issue though? What's the main problem with wind and solar? So for one thing, the sun goes down at night, and that sounds like a trivial thing to say, but it's actually a pretty big problem when you think about it in terms of these power demanded and power supplied by a system. If you were imagining some totally 100% wind and solar system, the fact that you're getting no energy from the sun at night is a problem. So that means first, you can't have just solar power, at least not without storage. So you'd want, solar power, and you'd also want a complementary source of power like wind. So if you put wind on here, wind does not decrease to zero at night. It does have a kind of a minimum in the wee hours of the morning, but it's much more consistent throughout the day. So that gives you more consistency in your energy. But in the way that I've drawn this here, you still have this, you have this problem where you have this mismatch where you have more you have more total power than you need in the afternoon, and you have much less than you need at night. And so a big component of these renewable energy systems is that you have to have a lot of storage. You need to have batteries, whether that's pumped hydro or you're pumping water up and then you're releasing it later when you need it and spinning a turbine and generating electricity that way. Or if it's lithium ion batteries, you need something to store that energy to move it past the peak time of the day and towards the night. So taking that energy and moving it to a time period when you're matching demand better. So the way that I've drawn this here, though, we still have unmet demand during this time period in the middle of the night. And so all that, the point here is just to say that you need a lot of wind and a lot of sun in order to have way more energy than you need during the day. And then you need a lot of storage to move that to the time periods when you essentially don't have sun. And so that means that this system that we're envisioning here is very intensive in terms of materials, in terms of land. So it would require several percent of the United States by land area to be covered by wind and solar panels. The wind, it's a little bit interesting with the wind farms because there's, do you count land use by just the column of the wind turbine, or do you count a wind farm as the entire, wind farm? So if you can do multi-use things with farms and things like that, then the land use looks a lot better. But if you're thinking about a wind farm as the entire area covered by wind turbines, then you're talking about like multiple states worth of land of wind farms in order to get enough energy to have 100% wind and solar power. So basically in this research, what I'm doing is I'm envisioning an electricity grid that has kind of overcome this day-night problem, this diurnal problem with wind and solar power. So I'm envisioning there's enough storage to move the surplus energy from the afternoon to the nighttime, and there's enough wind and solar power to essentially meet all of the energy needs. And then the electricity grid itself is more or less this whole area. So my domain here is Western North America. And so the reason for that is that you want to have enough, you want to be pooling over a large enough area so that when it's not windy in one of your locations, it's windier in one of your other, say, wind farm locations, or at least they're not correlated with each other, right? Because you don't want all of your wind farms to be not windy at the same time. And so vice versa would work as well. If it's not windy here, you want it to be windier here so that you're not actually changing your total wind power. And then same thing with your solar resource. If it's cloudy here, you'd want it to be extra sunny here. And if it's cloudy here, then you'd want it to be extra sunny here. And so the kind of base state that people are planning for is that you need a grid that's at least as large as kind of our current electricity grid. So this is more or less is the footprint of the Western Interconnection electric grid. And so we think that, a wind and solar system would need to have a footprint at least this large so that you are dealing with this issue of correlation properly, so that you have resources spread far enough from each other that they're not correlated or potentially anti-correlated. Okay, so starting from that case, the idea here is what happens if you have a solar power drought over the entire domain at the same time? So what's going on when it's cloudy over your entire domain at the same time, your entire electric grid? So that would be, you're reducing all of your solar power at the same time. And similarly, what's going on, meteorologically, if you have a wind drought or reduction in wind over the entire domain at the same time. So taking this and reducing all of your wind. And so I'm trying to get at, like we've planned for all of this kind of day-night variability and everything, but like what is the meteorology and climatology behind these ultra bad scenarios where you have widespread reductions in wind and sun over a large area and over a large period of time? So in what I'm going to show you over the rest of the talk is averaged over an entire week and averaged over this entire domain. And then of course you can also look at this in terms of what's going on if you have a reduction in wind and sun at the same time. So it's cloudy and not windy. Why would that happen? And looking at the reasons of why that would happen hopefully would help us prepare for forecasting that or anticipating that in some way or another. So what I will be showing you is kind of just looking at the circulation and kind of the correlation between these different variables, wind and sun. And then I don't really talk about it too much, but also the thermal aspect of things is important as well, because if you have a reduction in wind power, a reduction in solar power, and let's say it's also really hot at the same time, then you're going to increase your demand for electricity at the same time that you're decreasing your supply of electricity. And so this is an interesting time in human history, because we've kind of been moving continuously from a state of being less sensitive to the environment over time, where this is now transitioning to a period where we're being like more sensitive to the environment, and we have to plan for that. So as a meteorologist, I teach synoptic weather forecasting. And so I think everyone kind of has an intuitive sense that, sun and wind have a relationship with each other. And I think, the base case first approximation should be that when it's cloudy, that tends to be a situation where it's more stormy, right? You have like a low pressure system, you have a storm, it's cloudy, and then that's associated with more wind. So I think our base case expectation should be that when you have a wind drought, as in it's not very windy, then you should have a solar surplus and vice versa. So that's kind of exemplified by this graph here, that if you have wind power down here and solar power here, when it's windier, we would expect that to be a time period when you have less sun, because that's kind of like, this is the stormy situation. This is the low pressure situation where you have a low, you have a storm, it's windier, and it's not very sunny. And then the high pressure situation is this. It's it's not very windy, but it's sunny. It's a clear, calm day or week. And so one of the things that I'm interested in with this study is, when we actually look at the data, and we look at ERA reanalysis data from 1980 to 2020 in this study. So 40 years of data. When we look at this, does this kind of conform to our first order expectation? Because when we actually do look at the weather, like, of course, it's not always like this. Like, you do experience windy days that are very sunny, and you do experience calm days that are cloudy as well. And so we want to see if these wind and solar, if these times with low wind and solar power kind of conform to this first order expectation, or if there's kind of weird idiosyncrasies around them. Okay, so I am going to show some results here now, moving into the actual meteorology and climatology of these things. And this is like kind of a documentary study. We're just kind of documenting what these things look like. So this is kind of our first orientation of what's going on. So this is aggregated over the entire Western North American domain here. This is solar power and wind power. So we have solar power in yellow and wind power in green. And we're looking at the weeks of the year. And this is averaged across all of the years in the data set. So 40 years. So it's like each week has 40 years associated with it. So this is starting January 1st. This is the summer solstice when the sun peaks, and then back out to the end of December. And so both of these are normalized by their long-term mean, so proportion of long-term mean percentage-wise. And so what do we take away from this? Well, unsurprisingly, there's a very strong seasonal cycle in the incoming solar radiation. I think I was surprised, though, just how dominant the seasonal cycle is over the weekly variability. So this is the 2 standard deviation range in terms of, this is surface solar radiation pooled over the entire domain. So I'm not putting like imaginary wind farms or solar farms in various locations. We're just ignoring all of that complexity and just looking at the raw resource over the entire domain. And we can see that the seasonal cycle is just totally dominates any type of cloud variability in terms of how much sun you're going to get at any given point during the year. And that's not the case with wind. So with wind, you have very large week to week variability. And we do have this dip where we have a minimum where we're at about 60% of our typical wind value, basically in late summer. And so that the wind tends to follow the temperature seasonality. So it's lagged behind the solar seasonality by about 5 weeks. But so I guess the 2 takeaways from this are that the solar variability is totally dominated by just the seasonal cycle, wind variability much less so. But then the other thing is that you can see that these are slightly anti-correlated. So on the seasonal timescale, that means that it's good to have both wind and sun in your energy mix because you want things that are anti-correlated with each other to kind of diversify your portfolio and to have more constant total energy resources. Just looking at the maps of these, so like in the during the peak time period for solar during summer solstice, there's very little meridional gradient in the top of atmosphere incoming solar radiation at that point in time. So you're really, all of your gradient is dominated by clouds. And so we have kind of our highest value for a resource in the Southwest where it's least cloudy. And then when you look in the winter, that's a time period when the meridional gradient in the solar resource at the top of the atmosphere is dominant over clouds. And so you just kind of see that where it's sunnier to the south and you have less sun to the north. Looking at the wind resource, our wind resource is largest on the lee side of the Rocky Mountains. And that pattern doesn't really shift around during the year. It just kind of intensifies. It stays where it is and it intensifies or it gets weaker. So that's kind of our base resource that we're looking at. And then what I want to do is look at the extremes. So when you have extreme reductions in wind power and in solar power aggregated over the entire time period. And I refer to those as droughts. There's an important caveat to that. So droughts in hydrology typically refer to deviations with respect to the average seasonal cycle, right? So in California, where I am, it doesn't rain all summer and then it rains in the winter. And we don't say like we go into a drought every summer and then the drought is gone every winter. Droughts are always relative to the seasonal cycle. Here, I am defining droughts relative to the long-term mean. And the idea is that with the future energy system, we don't care all that much about the seasonal cycle or about deviations apart from the seasonal cycle. We care specifically about how much energy is available. So with hydrology, a lot of times you're thinking about systems that are already adapted to the seasonal cycle, where here we're thinking about creating a system that's just going to be most robust to the largest absolute lulls in those resources, in the wind and solar resources. So the way that I defined droughts here is just first percentile weeks over the entire data set. So because there's roughly 40 years in the data set, first percentile weeks are weeks with return periods of roughly 2 years. So a lull in the wind or solar resource that would be something that you'd see about once every 2 years. And we can see these on the screen here. So the wind droughts are in these circles and the solar droughts are in the squares. And so it's picking out the weeks, the 20 weeks, where the wind was in the first percentile. And so there's also plotting on top of that what the sun resource was doing during that same time. So we can see that the wind resource, we have these drought periods when the climatological wind tends to be the lowest. And then we can kind of see like what's the sun resource doing at that time. Like tends to be on this climatological mean or maybe a little bit larger. So you have a situation where seasonally the sun is larger or there's more sun than the long-term mean. And then also synoptically, you have more sun than the long-term mean. So just the weather of the situation means that you're going to have slightly more sun. And similarly with the solar droughts are confined to near the winter solstice. But the wind during that time period tends to be a little bit higher than what you would expect by just random chance. So in the interest of time, I'm going to skip this and show you. Okay, so here, this is a scatter plot of all of the weeks in the whole time period. And so what we're looking at here is the kind of the seasonal cycle in both our wind resource and our solar resource. And so you start here on January 1st and you move up this time period, and this black line is there's 52 of these dots. So this black line is the average for each week of the year. And then all of the individual dots are each individual week. And so we have a slight skew from the bottom right to the top left. So that's kind of showing our seasonal anti-correlation between the wind resource and the solar resource. We would love to have this be very anti-correlated so that they're like kind of perfect complements to each other. But it's just slightly anti-correlated. And we do see that when we have, for example, when we have a so this is the mean wind and solar power given a wind drought. So it's conditional on a wind drought. So it's saying if we have a first percentile week in terms of the wind, that's what these circles are. What is the sun doing? And let's draw on here. So we're saying we definitely have a wind drought. And what is the sun? The sun tends to be higher than average. So the sun is going to be close to 40% above average during a wind drought. And then we can also do the opposite and say, okay, when we have a solar drought, what's going on in terms of the wind? So this is demonstrating that you have a solar drought because it's way down here, but then the wind tends to be larger than average. So you have close to a 20% above average wind speed during a solar drought on average. So this is showing that these things are complementary, and you want to have both of them to be robust against these extreme lulls in one resource or the other. And then the worst case scenario is if you have a wind plus solar drought. So then you're down here, and we want to kind of know when those occur. And so it seems like those occur essentially it's like close to the winter solstice, when you have low seasonal solar output, and then you just happen to get a wind drought on top of that. So you happen to get a weather situation where you have very low wind in the middle of the winter, when you are going to have low sun anyway. Okay, so looking in more detail at the actual meteorology of what's going on during these time periods. The way that I did this was take all of these, for example, wind drought time periods, all of these weeks, and then just make a composite over all of them to kind of highlight what are the big patterns that we see. So this is conditional on a wind drought. What is the wind power? So we have green would be above average in terms of the anomaly relative to the seasonal cycle, and purple is below average. So what this is saying is no surprise when the entire domain on average is below, is in a wind drought state. We essentially have all of the area within the domain tends to be below average. And then what does the sun look like during a wind drought? It's conditional on a wind drought. The sun is kind of interesting. We have a kind of a dipole pattern where it tends to be cloudier than average to the southern part of the domain, and sunnier than average on the northern part of the domain. But overall, it's sunnier than average. And then this is that kind of thermal component that I'm not going to be talking a lot about, but this is showing that when you have a wind drought, it tends to be warmer than average to the north and cooler than average to the south. And this would actually be good for the energy system in this case, because this is happening during a time period when down here in the southwest or southern part of the domain, that's when you would have like a lot of cooling demand, because this is in the summer. And if it's cooler than average, then that's helping you out. Okay, so we want to understand the kind of atmospheric causes of this. And so one typical way of doing this is like the very canonical synoptic meteorologist way of looking at this, is that you look through the different levels of the atmosphere, starting at 200 millibars, looking at the jet stream, and kind of observing what's going on here. And so what we see is at 250 millibars, this is the top of the atmosphere, or top of the troposphere jet stream. We see that we have a jet streak here. So this is kind of an enhanced area of wind. So I have wind speed colored here. And interestingly, this location is called the left entrance region of the jet streak. And this is a location that is very typically associated with high pressure, downward vertical motion, and kind of calm conditions. So we're seeing something from the very first kind of map we look at, we're seeing something that we would expect to see during a wind drought. So stepping down further in the atmosphere, this is 500 millibars. So this is kind of the middle of the atmosphere. And we're looking at anomalies in terms of the height of this 500 millibar surface. And so these brown regions are above average heights and the green regions are below average heights. And so we basically see just an anomalous ridge, an anomalous high pressure system centered over British Columbia associated with these wind droughts. And this is stepping down further. So this is 850 millibars. And basically what we're seeing is that this high pressure system is a thermal high. It's essentially, it's warmer than average throughout the atmosphere. And so that is causing higher than average heights in the middle part of the atmosphere. And then this is interesting because we wanted to see, is this being forced from sea surface temperatures, for example? And you do see like a pattern emerge here of kind of like a positive PDO pattern, and then also maybe a negative Eastern El Nino pattern. But the stippling here is locations where the anomaly, where over 75% of the weeks have the same sign of the anomaly. And so the lack of stippling throughout most of the ocean, to me, indicates that this is not really an oceanic driven situation in terms of what the atmosphere is doing. It seems much more like this is just internal dynamics within the atmosphere that's happening to cause a wind drought. And there may be some, it looks like there is some association here with maybe an enhanced solution low and positive PDO, but it's not a very strong signature. And if it was, then we would expect to see just a bunch of stippling. And when you look at each one of these weeks individually, you see kind of a wide variety of patterns. So it doesn't appear that at the weekly time scale anyway, that this is really driven by ocean atmosphere coupling. It seems more like it's just internal atmospheric variability that's driving this. Okay, so one thing that we use to diagnose kind of the first step in the physical chain of causality, kind of going backwards in terms of what causes these highs and lows, and thinking about what are the main mechanisms driving these systems, is the quasigeostrophic omega equation. And so quasigeostrophic omega equation basically it's an equation that tells us the causes of upward vertical motion in this kind of highly simplified framework, which is quasi-geostrophic. So, but you can just think of it as we're assuming mostly geostrophic balance. So Coriolis force is balanced with pressure gradient force. And we're thinking about what causes upward and downward vertical motion in a framework like that. And so you got a bunch of terms, you got constants, you got derivatives. But the important aspects of this are you have advection by the geostrophic wind, and you have absolute geostrophic vorticity and essentially thickness. So those are our two terms that we use all the time to kind of diagnose what is the cause of upward vertical motion and downward vertical motion, and thus highs and lows in the atmosphere. Is we're looking for advection of vorticity and advection of basically anomalously warm or cold air. So warm air advection or cold air advection. And I'll just show you quickly, why this works. So thinking about absolute geostrophic vorticity, what this is this is the height field. And so you're looking at the Laplacian of the height field, which is essentially you're looking at the convexity of the height field. And then you have, your planetary vorticity here. But so this is saying if you have positive vorticity, positive absolute vorticity, that in this framework implies a convexity of your height field. And then if you are advecting that vorticity, and we have this vertical gradient here. That means that that convexity is actually increasing as you go up in the atmosphere. So sorry, I didn't mention that this is vertical in the atmosphere. So we often use pressure as a vertical coordinate, and then this is just a horizontal X or Y. But this is saying that if you have positive vorticity advection increasing with height, that is going to imply that you have kind of a compression of your geostrophic height, your barotropic surfaces. And the way to get that in this framework, like the kind of first order way to get that, is through upward vertical motion and expansion of air parcels and cooling. So that cooling is then what compresses those height gradients together. And so then the opposite is true too, that negative vorticity advection is associated with downward vertical motion, compression, and that the heating actually expands the space between those height contours. And then similarly, this other term, warm air advection, is associated with an expansion of the distance between the geostrophic or the geopotential height contours. And so then kind of a secondary circulation emerges where upward vertical motion is associated with warm air advection because you have divergence aloft and convergence closer to the surface. And then cold air advection is associated with downward vertical motion because you have convergence aloft and divergence near the surface. So that's just a brief explanation of why we tend to use vorticity advection and warm air and cold air advection to diagnose the causes of upward and downward vertical motion in the atmosphere, which are just fundamental to essentially high and low pressure systems. The low pressure systems and clouds and wind are associated with upward vertical motion, and high pressure systems, calm, sun, is associated with downward vertical motion. So we can kind of test to see, does this work in terms of our wind droughts? And what it seems like is it more or less does. So what we have here, this is during a wind drought. This is relative vorticity, which we often use as kind of a proxy for this geostrophic vorticity advection. And it's at 500 millibars. And so we assume that there's very little vorticity advection near the surface. And so whatever's happening at 500 millibars is going to be representative of this vertical derivative. But what we're seeing here is that we have negative vorticity here and positive vorticity here. And so you have negative vorticity advection right over that region where the wind resource is the strongest. And so that should be associated with downward vertical motion and calm winds, so less winds. And so that seems to more or less work. And then when we look at the thermal advection term, there's not a whole lot going on actually. So our wind vectors are small, and where they're large, they're kind of parallel to the isotherm. So it seems like it's the vorticity advection term that's dominant there. And so essentially what this is saying is that our wind droughts are kind of right in line with our canonical expectation of what we typically think of as just, you basically have a high pressure system over the western portion of the United States, or you have a couple over the period of a week, and you have convergence aloft and you have downward vertical motion, and this is associated with negative vorticity advection. And so that's kind of good news in terms of, being able to anticipate these things or forecast these things going forward, if they kind of align well with our pre-existing models of how the atmosphere works. And then that would mean hopefully that, lower resolution models like climate models should be able to represent these things as well. And so I will just tell you in the interest of time that we did the same thing with solar droughts, and solar droughts are essentially the exact opposite. So instead of a high pressure system over the West Coast of the United States, you have a low pressure system kind of sitting off of the West Coast. And so that's advecting moisture and clouds into the region. And so again, this is kind of right in line with like our baseline expectation at the beginning, that a solar drought would be associated with clouds and enhanced wind, because it's essentially a storm situation. And then the last thing we looked at was compound wind and solar droughts. And compound wind and solar droughts are essentially the exact same meteorological setup that we found for wind droughts, except they happen to occur near the winter solstice. So they occur during a time period in the season when there's very little sun, but the meteorological setup is almost exactly the same. And so I'll actually just, if we look right here, I'll toggle back and forth between, so right here, this is a wind drought, and this is a wind and solar drought. Wind drought, wind and solar drought. So looking at those resources combined, and yeah, so it's the same atmospheric setup, but just occurs in the middle of the winter. So kind of our conclusions, our documentary study here, wind droughts occur in late summer, and it's basically a high pressure system set up over the western portion of the United States. And so then because it's a high pressure system, it's associated with subsidence and solar surpluses, so less clouds. And then basically aligns very well with what we would expect just from first order synoptic meteorological expectations. And solar droughts are essentially the opposite weather situation, but they are constrained to occur very close to the winter solstice, because the solar cycle is dominated so much by the seasonal cycle in the incoming solar radiation. And so our wind plus solar droughts, or our combined situations where you have a reduction in both, are basically a weather pattern like we saw with the wind drought, but occurring in the middle of the winter when there's very little sun. And so kind of our high level takeaways here are just that wind and solar power are complements to each other in terms of both in terms of the seasonal cycle, that you have more sun. You have more sun when you have less wind seasonally, and then also just weather-wise in terms of high and low pressure systems. And then, using this kind of framework of quasigeostrophic theory and the quasigeostrophic omega equation, we can see that kind of the first order, backwards moving. If you're looking at the chain of causality, you go back one link in the chain, everything kind of makes sense in terms of what we would expect in terms of the causes of these wind and solar droughts. And so they're not some strange idiosyncratic thing. There's something that we already know about. And so that should be helpful in terms of forecasting, both in terms of traditional weather forecasting, so days ahead, potentially seasonal forecasting. And then it's also good news in terms of thinking about climate models and how they might be able to simulate these phenomena going forward. Because if we can kind of represent them as a first order blurry, through geostrophic theory, then that's something that a climate model should potentially be able to simulate as well. So thank you.